And this will be involved gradually more kind of calculations, and then we will gradually upload the first homework, and the part of things can starting from here. Okay. This section talk about the spring elements, and we will talk about how to describe the spring of vibrating systems, and in particular, we will focus on the equivalent spring constant. Okay, so basically in these sections, our goal is to learn how to determine, how to calculate the equivalent spring constant of certain systems. And this graph is a copy from mechanics material. And basically this same is this. If we would have any continuous systems, for example, we start from here. Say, for example, this is a bar, and actually this is an elastic bar, and you know the elastic means that means it's deformable. Okay, deformable, that means it has the Young's modulus E, and it has dimensions L. For example, the length is L. Okay. And it has geometry and say a cross-sectional area A. So say this is a cross-sectional area A. Okay. So you know from the mechanical material, if we apply a loading F here, then this one will be deformed by delta. And if you still remember that calculation, delta equal to FL over EA, right? Okay. If not, that's okay. Just take it at this moment. So once you have these formulations and how to obtain the equivalent spring constant, so which means this one, how you're going to equivalently to describe this kind of continuous system into a discrete system. Let me call this the KEQ. Okay. So this one again we apply the same amount of the load. Okay, so that means, and again, this one, under the same amount of load, we're asking to deform at the same amount of the deformations. So that is called the equivalent descriptions of these systems. The same amount of the loading, the same amount of deformations. Under these situations, we want to determine FEQ. So you know Hooke's law, right? Hooke's law is F equal to spring constant multiplied with deformation. We have the force, we have the spring constant, we have deformation. Basically, this is Hooke's law. Right? And from the original system, we can re-describe, we can remove kind of the moving around the terms to make up this. So you see what happens here. So this one basically equivalent is this. I want to make up F and I want to make up delta. So from here can you see this one is F equal to EA over L times delta. I simply remove the three terms to this the same side of the delta. So that meaning this is our KEQ. Okay? You good? Okay, so we can look at another example here. So for this example here, and let me redraw here. That'll be clear. So for that example, say we consider different elastic system. So this system is such that we have the cantilever beam. Again, we describe by its material properties E, a moment of inertia I, and the length L, and using capital L. Okay. So that is the material properties and geometry and dimensions here. And for this one, we applied loading. For example, the loading applied at the end, the free end here, with the magnitude F. Okay. And we know from mechanics material, this is going to deform. which means it's going to deflect. And from the tables, this is from the table of the mechanical material. We know that the maximum diffraction that happened at where the loading applied the free end. So this one, then we call the Y, whatever. This one, basically this distance is PL3 over 3EI. Okay, the diffraction at here from we have learned, actually we knew how to do it, and basically we can calculate that is that much. So let me define this called the delta. Okay. So if you're going to use this beam, set it up as equivalent to, say, something like this. Is a KEQ. So say, let me describe this one under the same loading. And doing the same deformations, for example, from here to here, is delta. So what is KEQ? Again, from Hooke's law, F equal to KEQ times delta. And this one you can see, this F, then I simply replace the F. The P representing is the loading. So basically the P should be equal to F. So let me rewrite here. So basically this is F L3 3EI. I simply replace the P, which is the loading, by F. Okay. So from here, I simply rewrite. So F equal to, using this equation, will be equal to 3EI divided by LQ. So from here, you compare the KEQ equal to these numbers. You okay? So which means this such a system described is this. So if you're using the cantilever beam, something like the crane, say in the structural engineering or civil engineering, they're using crane to lift the batch of the steel bars. So say this is the mass here. Okay, and because this is elastic, so this one you can describe by such a system. KEQ is given by this number. Be good? So this is, we try to discretize, we try to approximate this continuum system into a 1 degree of freedom vibrating systems. And under this case, we have a problem statement like this, then we can proceed the formulation into differential equations and then into the solution. Then we can have the preliminary analysis result to this real system here. Okay, so the similar concept, probably you can try to learn, try to go ahead. And again, for this kind of the continuous systems, most of the information are available from your textbook, the mechanical material. Okay, you see those kind of formulas here is from there. And you simply put into the format of Hooke's law, F equal to K delta. There, naturally, the natural frequency, the equivalent spring constant will coming up. Okay, and so probably let's do more on coming Friday. Okay, so we will continue this section.